Hey everyone, I'm going to do a quick lesson on momentum and how it relates to rocket science, given this week's rocket launch, which is pretty cool. I think it's a topic which we sort of gloss over because we didn't really have time to dive all the way in on momentum. But I wanted to mention it because it's something that I think we often overlook. It's very much a direct application of that conservation of momentum that we've been talking about in this really cool scientific way. So here we have a rocket, and I've learned just to use clip art of rockets rather than trying to draw rockets. That's a physics teacher lesson that happens. But if we say this rocket has a mass, and I'm just going to make up a mass, I'm going to say 3,000 kilograms, which is a lot, but probably nothing compared to like the millions of kilograms of like an actual NASA rocket, but that's fine. And we want to get this thing, right now it's on the ground, so here's our ground. It's just like sitting on a hillside. And we want this to reach a velocity where it can actually be in orbit around the Earth. And I'll tell you that an orbit like that is going to be thousands of meters per second. So it's something like 17,000 miles per hour is what the International Space Station is moving horizontally around the Earth in order to stay in orbit. So we'll say that this thing needs to reach a velocity by the time that it's like actually up here. It's going to reach a velocity of, let's say, 8,000 meters per second. Okay. Now, right now, the initial velocity is 0 because it's just sitting there on the ground. So when we talk about rocket launch, right, a rocket launch is going to involve burning some sort of fuel, and we'll get some sort of like fire coming out the bottom. That's not a very good color for fire, but that's okay. Let's see, fire shooting out the bottom, and then it goes up, right? And if you stop and think about that before we give away the answers, think about like how is it going up? Yes, there's fire coming out the bottom, but why does that translate into the rocket moving up? And some of the ideas that might first come to mind is that, well, it's pushing off of the ground, right? That it's pushing off of the ground, and as Newton told us, that when you push something one way, the other object goes the other way. And to some extent, sure, there's some interactions happening here that are against the Earth, but as soon as this rocket has sort of cleared the tower and sort of cleared the Earth being immediately beneath it, it's still able to go up. And then you might say, well, it's pushing off of the air. Okay, that's fair. But then when the rocket gets to space, where there's vacuum, there is no air, it's still able to fire its engines and move itself around and accelerate and decelerate and all those things. So what we're actually looking at here is the primary action is not so much the rocket pushing against something else that's outside of the rocket. Instead, what's happening here is there's a propulsion of exhaust and of this burnt fuel in the downward direction. And just to simplify this, we'll take like the primary ingredients of rocket fuel these days is liquid hydrogen and liquid oxygen. And if you're a chemistry savvy person, you could say, well, if we have H2 gas and we have O2 gas, then we can actually produce H2O. And let's see, can we balance this? We balanced it. Look at that. So for every two H2 gas molecules, for every one O2 molecule, when you burn those, you combust those, they actually form water. And what's kind of incredible is that primarily what's shooting out of the bottom of a rocket that's using these two fuels, or that's burning the H2 using oxygen as the fuel, the thing that's shooting out the bottom is actually water molecules, which is kind of wild. Now, that doesn't mean like stand under it. It's like a fun sauna. No, those are coming out at extreme crazy temperatures because hydrogen is very, very ready to burn, to ditch its fellow hydrogen and to glom onto those oxygens. It's very happy to do that. It's a very explosive and quick reaction, and tons of energy is released. And in that process, those water molecules get shot out super fast. And so when we bring this back to momentum and think about it, what's happening there is these tiny little water molecules, which individually have these teensy tiny little masses, are getting shot out with relatively pretty fast velocities. They are getting shot out with crazy kinetic energy. And because of that, that is momentum happening, being given to these water molecules in the downward direction. Now, because momentum is always conserved, if you're shooting this exhaust out the bottom of your rocket in a downward direction, then your rocket's going to gain momentum in the upward direction. And it's a complete conservation, which is why you need to bring that fuel with you. You need to have that fuel in order to shoot it one way to push yourself the other direction. And if you look up some of the statistics about just how many millions of pounds of fuel are needed in order to launch just a relatively small payload up to the International Space Station or wherever, it seems crazy how most of the weight of an actual real-world rocket is just the fuel. But the fuel is everything to this, that you need to be able to shoot that fuel very, very quickly downward through the process of exploding it in order to launch it upwards. And it's honestly not that different than if you just took a balloon and blew up a balloon and then you let go of it and it goes zipping around. Well, those air molecules, because of the elasticity of the latex of the balloon, it's pushing those air molecules that way, which is going to push your balloon in the other direction. It's that same conservation of momentum. It's just that when we're actually doing it and launching people into space, we have cooler fuels that can shoot things much, much faster. And much, much heavier things as well. So that's a little bit about what's going on with momentum as it relates to rockets. Okay, so I took a Estes model rocket out with my children and we set it up. And this is the cheapest possible model rocket kit that a person can get. You only really need to put the pieces together, following the instructions, and then you hit go. But what it is a rocket. You've got a little stand here. The engine is it's like a black powder, which is sort of like a gunpowdery kind of material that's set to burn at a fixed rate. It propels itself by shooting those chemicals, the exhaust of that chemical reaction, downward. So it channels it downwards, which then pushes the rocket itself vertically upwards. And that's all there really is to it. At the end, there's a little pop and a parachute comes out, and then you have to go and run and find your rocket. But that's pretty much it. Okay, so here we go.
3, 2, 1. I can't. It's so slow from here.
Yeah, we may never see that again.